Hello everybody and welcome to the part 2 lecture of hypothesis testing. In this lecture we're going to pick up right where we left off from the previous lecture, and we're going to run through the same example from the last lecture, but this time we're going to do a two-tailed test. We're also going to increase the alpha to 0.01 from 0.05. So instead of being 95% confident in these results, we're going to crank that up to 99% confident. And we're also going to be testing this on both tails of the distribution. So when alpha is set to 0.01, we are 99% confident when rejecting the null hypothesis. And for a two-tailed test, we have to make sure that the size of the tail is equally distributed. So whatever we're setting our alpha to, in this case 99%, that means that the alpha is going to be 0.01. All we have to do is divide that by 2 because we want equal proportions in the tails. We want equal-sized rejection zones on either side of the mean. So simply we take 0.01, we divide that by 2, and we end up with 0.005. So what z-score do we need to obtain to have 0.005 on either side of the distribution? Well, we would do the same exact thing that we did in the previous example. So we want to have 0.005 in the tail. That is our rejection zone. We know that 50% of observations are to the right of the mean. So really all we have to do is take 0.5000 and subtract 0.005 from that, and we end up with 0.4950. So that's the shaded region that we have to find in our z-table. So we look through our z-table and we're looking for 0.495, and we're looking and we're looking. And so we isolate this row. Okay, we see that we've got some numbers here. We've got 2.5, and we run all the way through that row looking until we get to 0.495. And again, we kind of have the same situation. We've got 0.4949 and we've got 0.4951, so not perfectly 0.4950, right in the middle. But we're always going to go for the critical z-score that's a little bit harder to meet. So we're going to go with 2.58 right here because it's a little bit more than 99. And again, I think it's just a good idea to understand what it is exactly that we're doing, and looking up the shaded region in the z-table and understanding that the inverse of that is what constitutes the rejection zone. But if you would prefer not to have to look up in the z-table for these critical values, it's very easy to remember what the critical z is for different alpha levels, and obviously those are different for one-tailed tests and two-tailed tests, because with the two-tailed test we're dividing that region into two tails. So the critical z for an alpha of 0.05 with a one-tailed test is always going to be 1.65, regardless of the size of your sample. For an alpha of 0.01, that critical z is always going to be 2.33. And with a alpha of 0.001, if you want to have that strictest measure of confidence, you want to be 99.9% accurate in your results, you're going to use a critical z of 3.1. And then you can see the other critical z's with the two-tailed test. So these critical z's will always be the same. Again, remember, these are standardized values. They never change. They're with respect to the normal distribution. So if you would like to, just make a note of what these critical values are, this is a very good resource to have. So when we set alpha to 0.01 and we're doing a two-tailed test, we are using a z statistic or a critical z of 2.58. This means that there is a rejection area of 0.005 on either side of our distribution. So basically our critical z is negative 2.58 and 2.58. So we don't really have to care about the absolute value of our observed z when we're doing a two-tailed test. So all we have to ask ourselves is negative 15.21, is that higher than negative 2.58? Or is it higher than positive 2.58? And yes, obviously, we have found a very massive observed z-score. Obviously, that's much higher than negative 2.58. So even with 99% confidence, we know that we are completely rejecting the idea that that true population parameter is 5. And again, just to give you a graphical representation of what we just did, we have a more strict threshold, 99% confidence. So you can see that we've put the rejection zone on either side of the distribution. And we do this when we don't know, what direction our sample mean is going to be in. And sometimes that's the case. We don't really have directionality. We just want to test whether two things are significantly different from one another. So this is just kind of illustrating how you can have rejection zones on one tail or on two tails. So again, we have that massive observed z of negative 15. Obviously, that is very far away from the hypothesized population mean, and we find evidence supporting our alternative hypothesis, and we reject the null hypothesis. So just to do a quick recap on statistical inference so far, last week we learned about z-scores. Now those are used within samples, so we're taking sample scores of interest and we're subtracting sample mean from those scores of interest. Today we've talked about test statistics. These are used to test a sample against a hypothesized population parameter. So here we've been subtracting hypothesized population parameters from the sample mean. And then we also talked about the equation for calculating standard errors, which is simply the standard deviation divided by the square root of n. So these are some very helpful equations for you to make note of. So far, we've only really discussed large sample hypothesis tests. So generally, when we have an n of greater than 50, we're going to be using z-scores and z-statistics and things like that. And as we've discussed, large sample size data generally falls on the normal distribution. We've talked a little bit about small sample sizes and how those don't necessarily conform to the shape of the bell curve. And I know everyone in this class should have at least 50 observations in their data set, so I'm just going to briefly go over the t-distribution just so you understand. I think some students have subsets of their data that they want to make comparisons with. So you might have a subset of observations of maybe 20 or 30 that you want to compare variables on those specific attributes. And in that case, when your sample size is below 30, you'll be relying on the t-distribution. And again, the computer program is going to do all of this for you. I find it just to be helpful to understand the mathematics going on behind what the computer is doing, so you really truly understand how to interpret the results that the computer program is giving you. So let's just briefly go over small sample sizes and the differences involved in calculating statistics there. So we rely on t-distributions when n is less than or equal to 30. What's important to note here is that you can see the t-distribution is much fatter and wider, and it allows for way more observations to fall within the tails than would the normal distribution. And the way we calculate means test with samples and hypothesized population parameters is very similar, regardless of whether we're using t or z distributions. There's just one minor detail that we have to discuss. So as always, you would choose your alpha, what level of significance or confidence you would like to work with. You have to find the degrees of freedom. That is the one thing that is unique about the t-distribution. Degrees of freedom are simply denoted by your n, your sample size, minus 1. Then we have to look in the t-table and find the critical values. And then we calculate the observed t, which is the exact same equation that we used for our z distribution. So it's the sample mean minus the hypothesized population mean divided by the standard error, which again is the standard deviation divided by the square root of n. So imagine we're answering that same question from the part 1 lecture. You want to debunk your friend's hypothesis that Americans are more conservative. The population parameter remains 5, but suppose we were only able to collect a sample of 25 people. We're going to set alpha to 0.05. We want to stick with our 95% confidence. Now the first thing that we have to do is calculate those degrees of freedom. So we know that degrees of freedom is calculated by n minus 1. We see that our sample size here is 25, so 25 minus 1 equals 24. And all we have to do, instead of the very complicated z table looking up and calculating proportions and determining what's in the rejection zone, all we have to do is look up the degrees of freedom in the t table. So it's super duper easy. So we look here in the first column. We look for the value that corresponds to our specific problem. So we know that we have 24 degrees of freedom, and then we just have to pick the value that's most appropriate. So you can see the very top row here is asking us if we're dealing with an alpha level for a one-tailed test, or if we're dealing with an alpha level for a two-tailed test. We're just going to do a one-tailed test because we're pretty sure that the sample mean is going to be lower than 5. So we're just going to stick with the one-tailed test. We're only concerned about what's to the left of the mean. So we pick our alpha that corresponds with 95% accuracy. The inverse of that would obviously be 0.05. So we stick with this first column here and the row 24. So that gives us a critical t statistic of 1.711. And again, as long as our observed t statistic is greater or equal to our critical t that we just looked up in the table, which was 1.711, then we can reject the null hypothesis. So we analyze our data with our sample of 25, we calculate the average, and we find that this average is 4.44, and we get a standard deviation of 1.23. Now all we have to do is just plug that into our equation. We take the sample mean, 4.44, we subtract that by the hypothesized population parameter, which is 5, and then we divide that by the standard error, which is, again, we have all the information we need to calculate that. We have the standard deviation, and we're going to divide that by the square root of n, which would be 25. So here we've plugged everything in, 4.44 minus 5 divided by 1.23 divided by the square root of 25. We do some math. We do some more math, and then we get our observed t, which is negative 2.28. So again, we take the absolute value of that, and we have to ask ourselves, is it higher? Is it greater than or equal to critical t, 1.711? Yes, it is. We can see that our observed t from our sample is much higher than that critical t. And we can reject that null hypothesis. And even with our very small sample, we were still able to reject that null hypothesis. So just to show you a little bit of the differences with the t distribution, we're not working with our very pretty bell curve anymore. We're working with something that's kind of like a half circle distribution. So you can see that the tails are much wider, far more observations fall in those tails. But we know that our hypothesized mean for the population is 5. We created our rejection zone based on our degrees of freedom. So we ended up with a critical t of 1.71. And basically what this is saying is that, 95% of observations are to the right of this point, and 5% of observations are to the left of this point. We calculated the statistic for our sample, and we found that that was negative 2.28. So we think about all of these things in terms of absolute values. Is 2.28 greater than critical t, 1.71? Yes, it absolutely is. It always helps to just, work through these problems by shading in rejection zone regions and plotting points and drawing a line where your critical T is. And if you follow these steps, you can, the absolute values might be a little bit confusing. If you're on the left side of the mean and you're working with negatives, it can be a little difficult to maybe always remember whether or not a observed value is in fact higher than a critical value. But just shade the distributions, and I think that you'll always be in a situation where you get the right answer. So obviously we see that our sample mean is falling in this rejection zone, so we're pretty confident that this whole population parameter equaling 5 is just not accurate. So in both cases, we were able to reject that null hypothesis in favor of our alternative hypothesis that Americans do not lean conservative. So just a really quick recap on our distributions. This is an exam question you'll certainly see on the final. When n is greater than 30, we use the standard normal distribution and our z tables. And when n is less than or equal to 30, we use the t distribution and the t tables. So just keep that in mind, how sample size correlates with the specific statistic that you have to use for that data. All right, now the last thing that we're going to do in this lecture is we're going to calculate confidence intervals, and these are pretty simple, and we have already learned all of the equations and statistics and things that we need to create confidence intervals. And confidence intervals really come in handy when we don't have a good idea of what the true population value might actually be. So in the previous examples, we were hypothesizing that the population parameter might be something. We were comparing our samples to see if we could reject or confirm that idea. And in both cases, we rejected the idea that the hypothesized population parameter was true. So when you don't have a good idea of what the population parameter might actually be, this is where confidence intervals come in handy. We take the standard error and we multiply that by a specific critical value to obtain a range of values. So we can be 99% confident that a specific variable's average is within a specific range, or we can be 95% confident that the true population parameter is within a specific range. Again, it's all really up to you and the type of or the level of confidence that you want to have in your estimates. So the formula for calculating a confidence interval is really simple. All we do is we calculate the mean of our variable, or whatever it is, the thing that we're interested in. And then we additionally, we multiply the standard error by the critical value, depending on our alpha and our threshold, whatever that is. And then we add and subtract that value to the mean, and then that gives us a range of values based upon our alpha. So let's run through a quick example. And I'm just going to do an example with no context, just so you can see the numbers and understand what it is that we're doing. So let's imagine we had a sample size of n, and whatever thing that we were studying, let's just say that it had a mean of 16 and a standard deviation of 3. And what we want to do is we want to compute a 95% confidence interval for this mean. So if we wanted to take this sample and we wanted to get a good idea of what might actually be true in the entire population, this is how we calculate that. So our sample size, n, is 100, sample mean is 16, standard deviation is 3, and we're setting our alpha to 95. So the first question we have to ask ourselves is, what distribution are we going to use? Are we going to use the z tables, or are we going to use the t table? And hopefully you can see that since we have a sample size of 100, that is obviously much higher than 30. So we are going to be using the z statistics here. So just as we've already walked through, a 95% confidence interval means that we will have 5% of observations in the tails. And remember, the z-scores use proportions, so we need to determine the z-score where 0.05 observations are in both tails. So all we have to do is take that 0.05 and divide that by 2. So that means that 0.025 is going to be on either side of our distribution. Those are our little rejection zones. And from our z-table handouts, we need to look and find the corresponding z-score of 0.5000 minus 0.025. So either you could look up the corresponding z-score when there's a point of interest to the mean that accounts for 0.4750 of observations, or you could just look back to that cheat sheet that was provided a few slides ago and know that a two-tailed test at 95% confidence, your z-score is always going to be 1.96. So we're just going to refer to the cheat sheet and see that we need to be working with critical z values of 1.96. The next thing that we have to do is calculate the standard error. So we know that that is the standard deviation divided by the square root of n. So we end up with 3 divided by the square root of 100. 3 divided by 10 equals 0.3. So that is our standard error. And now we have absolutely everything that we need to know in order to calculate a confidence interval. So I like to, obviously, the mathematical operations, we take our standard error and we're going to multiply that by our critical values. We're going to do that first because these are in parentheses, our order of operations. So 0.3 standard error times 1.96, which is the critical value, that equals 0.588. So all we have to do is add that to the mean and subtract that from the mean. And that's going to give us a range of, what we think the actual population estimates are. So 16 plus 0.588 equals 16.588, obviously. And 16 minus 0.588 equals 15.412. And that's denoted here in the brackets. What we do is we do one bracket, and then we type in the lower bound, and then a comma, and then we type in the upper bound. So with 95% confidence, we estimate the true population parameter to be somewhere between 15.4 and 16.5. And so you might be thinking, either you really liked that example because it didn't have any context and it was just the numbers, or you need some context and you don't really understand what we've done. And that's why I have one example remaining for the part 2 lecture. Okay. And now we are finally at the last example. If you want some context into understanding how we calculate confidence intervals, we're going to do that. And we're also going to work with a small distribution so you can see how we calculate our confidence intervals using the t-table. So suppose we would like to estimate the amount of money spent on school supplies each semester by UWL students. We gather a sample of 15 random students and determine that the mean was about $250 with a standard deviation of $50. So what would a 95% confidence interval of these estimates look like if we wanted to generalize and say, well, how much do all college students spend each semester on school supplies? So first of all, we have to figure out the N. What is the N of the study? We know that that is 15. What distribution should we use? Well, it's under 30. So hopefully you have gathered that we're using the T distribution here. We look up the T statistic in our table. Remember, we have to calculate the degrees of freedom. So 15 minus 1 equals 14. So we have 14 degrees of freedom. And understanding like the statistical principles of degrees of freedom is pretty complicated, and I don't think it's super necessary for this course, so I wouldn't worry too much about understanding the intricacies of degrees of freedom. I just know that you need to know how to calculate it, which is n minus 1, and how to use the t-table. So we see we have 14 degrees of freedom. We're going to look for the two-tailed alpha of 0.05, and we see that that gives us a t statistic of 2.145. Next, we need to determine the standard error. So we already know that the standard deviation is 50. We need to divide that by the square root of the sample, which is 15. So the square root of 15 is 3.87. We take 50, divide it by 3.87, and that gives us a standard error of 12.91. Now we have all of our values. We just need to multiply the standard error times our critical t statistic. So that's 12.91, the standard error, times 2.145, which is the critical t value. And when we do that, we get a value of 27.69. So really what this is telling us is that that's the amount of variation we should expect if we were to expand this study to the broader population of all college students. So we take $27.69 and we add that to the mean and we subtract that from the mean. So what this statistic here, this point and interval estimate is telling us is that if we expanded this study to the population of college students, we would expect them on average to spend approximately $222.31 to somewhere upwards of $277.69 each semester on school supplies. So I hope these examples have made sense. I know we've gone over a lot of different statistical procedures today. We are going to continue to work on these examples in class. We're going to start learning how to use Stata and using the shortcuts for calculating these statistics, so you're not doing everything by hand. But I truly hope that you understand the mathematical principles and processes behind these statistics. I hope that this helps you understand and interpret statistics from your own data when you're in class. Again, if you have any questions from this week's lecture, please don't hesitate to post those in the discussion board so I can take a look at those before class on Thursday. And as always, stay healthy, stay safe, and I will see you guys on Thursday.